I am going to go ahead and get started. Good afternoon to everyone, and welcome to a Decarb Healthcare Workshop. This one, like no other. The purpose of this workshop is to provide a fun way to interact with some draft sections of the guidebook. And so to make it fun and challenging, we've structured this as a debate. It's desiccant systems versus displacement ventilation. Which one is better for decarbonizing healthcare? Now we know, like most debates, this is kind of creating a false dichotomy, right? The real answer is that they both likely have a role. But we'll have fun as we champion one or the other and debate this topic. We have two champions that will meet momentarily. Jim Crabb for desiccant systems and Taylor Harms for displacement ventilation. So during round one, Jim and Taylor will each share a short presentation on their topic, and then they will engage in some light debate with me as the moderator. And then after round one, you'll enter a breakout room assigned at random, and we'll spend 20 to 25 minutes engaging with each other in the breakout room, using the guidebook and preparing for round two. And that's where the real fun begins. During round two, you'll have the opportunity in 2-minute sections to make arguments and counter arguments. And during that time, you'll notice, if everything goes well, that my box will include a timer that we'll use to help keep us on time. And we will have a lot of fun. You'll get to argue and banter, and we will not declare a winner at the end of our session, but you'll know which team won. I want you to know that for the best experience during this session, especially the breakout room, you'll want to join via computer. If you can't join via computer for some reason, you'll still be able to participate. Real quick, before I turn it over to Jim and Taylor, I want to share two quick slides. Those have 2 quick points to kick us off. The takeaway from this slide in 10 seconds is that the big energy consumer in hospitals is reheat. On the next slide, you'll see that the big takeaway is that climate does not significantly impact energy use at average levels of energy consumption. Those two might be 2 surprising conclusions, and you can look into the details from the Integrated Design Lab more if you would like. But those 2 points guide us to these debate topics because they both impact reheat and they might both be used in different areas. And so now I'm going to turn it over to Jim and then to Taylor to tell us more about these systems, and then we'll get into the debate.
All right, thanks, Troy. So hopefully those 2 images that Troy just showed us are not how hospitals are being designed today. That's somewhat historic data now. But the reason things are getting better is because of the kind of things that Taylor and I are here to talk about, and a lot of other things. So before we get started here, we had to do a little bit of psychrometric education. For the mechanical engineers among us, I apologize for this, but dew point is a term that is not used very commonly except among us mechanical engineers. Dew point has a very specific meaning, but for our purposes, we can think of dew point as an indicator of the moisture content of air. Independent of temperature, the temperature doesn't matter. The dew point tells you how much moisture the air is holding. And that's important because when you get to relative humidity, knowing what the relative humidity is doesn't really tell you a lot unless you also know the temperature, because the 2 are closely related. So dew point is more of an absolute moisture, and relative humidity is, as you might expect, relative to the temperature. Next slide. So what I've done here is looked at the climate zones that are defined for California. Kind of a crazy number of climate zones for one state. But the numbers you see tallied here are the number of hours at which the dew point temperature is, in the case of the yellow numbers, above 46 degrees, and in the case of the white numbers, above 55 degrees. Does anyone who's not a Mazzetti mechanical engineer Want to take a stab at why we care about 55 and 46? Why are those numbers important?
General areas and the ORs.
Exactly right. The dew point temperature at 75 degrees and 50% relative humidity is about 55 degrees. And the dew point temperature at 65 degrees and 50% relative humidity is 46 degrees. Those are the operative numbers for figuring out whether you're delivering the right and maintaining the right conditions in a space. So you see an awful lot of California. It's fairly dry, and the 55-degree number doesn't really matter much. We don't need to worry too much about dehumidification in Fresno for general areas. But for operating rooms where we're trying to maintain 65 degrees, even there it matters some. And that's because we care about the outside air, the moisture in the outside air. Next slide, Jess. So I apologize for showing you a psychrometric chart. Those of you who are not mechanical engineers, please just try to play along with me and pretend that you care what I'm talking about. So the moisture in our spaces comes from outside air. There's a little bit of moisture from other sources in a hospital, but for the most part, it's the outside air, because we know we ventilate hospitals quite a lot. So what I'm showing you here is the Atlanta condition, because it's a much more dramatic situation than most of what California deals with. And because I'm sitting in Atlanta, I can tell you. And so in Atlanta, our outside air dew point is 74 degrees for design. Actually, there are parts of California where the design condition is similar to that. You just don't have as many hours. And so if we try to take that outside air down to the condition we want in an operating room, 46 degree dew point at 65 degrees, you can see we're going down the chart and to the left on the chart. Left to right is sensible heat, and up and down is moisture. And you can see there's a lot more moisture involved, moisture that needs to be removed from that outside air to get to an operating room design condition. That's much more significant than the sensible heat that needs to be removed. Next slide. So again, another psych chart, sorry, but when we mix that air, our standard system for removing moisture from air is to cool it down. When we cool the air down, we reach the dew point temperature and we squeeze the moisture out of it. And that's what a typical air conditioning system is doing. That's what the blue line shows you. We're taking that mixed air stream, cooling it down, saturating it, getting down to about 46 degrees for an OR. And then we have to reheat it, because if we deliver 20 air changes of 46 degree air to an OR, it's going to get cold, too cold, and it'll still be high humidity. So we raise the temperature back up, and that's one example of where reheat is used all the time, 24/7 in most ORs. For typical spaces, it's not quite that dramatic, but ORs are a good example. So there's another way to do it. And just like the little packets that show up in almost everything these days, of course, you don't eat them. We use them to remove moisture. Manufacturers ship things with these packets to remove moisture from the package. We can use that same material to remove moisture from the air. Next slide. And basically, we're applying that silica gel to an aluminum substrate, or maybe plastic, and we draw air across it. And when the moisture content is high in the silica gel, it gives off that moisture. When it's low, it absorbs moisture. And so we can dry air without having to cool it down. It does require some reactivation air. We have to heat that air back up to reduce the relative humidity. But if we do that with recovered energy, we haven't really changed the picture that much. So next slide. So when we do this, what we're talking about is using that desiccant to remove moisture from the outside air. We would do that primarily in places where there's a significant number of hours where the dew point's above our design. Again, in a good bit of California, that might apply to ORs, but it probably wouldn't apply to general areas. This is a rotating wheel. It rotates through the airstream and then through the reactivation air. So there is some maintenance involved. It does require heating to regenerate the desiccant. Best practice would be, of course, to use recovered heat for that. And the other thing you want to pay attention to in any of these systems is some occupancy controls so that you're not dehumidifying when you don't need to be, when the humans aren't there. How does that decarbonize? Of course, it reduces the amount of cooling you have to do, and it reduces the amount of reheat you have to do. The cooling you're doing, of course, is generally electric, and that might be not very carbon intensive, and it's going to get better. The reheat that most people are doing in hospitals these days is still based on fossil fuels. So anything we can do to reduce reheat reduces carbon emissions. And so your strategy here is to pay attention. Look at your operating conditions, your dew point, and the climate. See how many hours you've got. Use a desiccant where it makes sense, and use exhaust air heat recovery. That's kind of another talk I'd be happy to do sometime. And then pay attention to the costs of these systems. If you're using a desiccant instead of cooling, you might be saving some money that helps offset the cost of the desiccant system. And I'll stop there.
Okay,
Next
thank you,
up,
Jim.
Take it away, Taylor.
Thank you very much. Displacement ventilation does exactly what it says. The cool air that is much closer to the room set point is brought in much closer to the breathing zone. And as the cooler, denser air fills up the room, it's going to displace the warmer, contaminated air and push it towards the ceiling returns. Because the air is put into the room much closer to the breathing zone, the ventilation effectiveness is much more effective, which allows you to use lower airflow rates. That combined with the warmer supplier temperatures leads to much lower reheat and cooling energy needed to condition the space. And this can result in a 31% reduction in cooling and 15 to 20 in space heating energy savings. Next slide. Here we can see a little bit of a demonstration of how it works. The contaminated air is brought out of the space much more quickly and isn't being mixed in with the rest of the air that's in the room, protecting the occupants inside. And something similar here as well. There's 2 less air changes required for the same amount of ventilation and contaminated air removal, comparing displacement ventilation to overhead mixing. There are many benefits of displacement ventilation, obviously. Reduce airflow, reduction in equipment energy. There's an increase in the availability of free cooling, less noise, decreased reheat, improves indoor air quality, which is of utmost importance for healthcare spaces especially, and improve thermal comfort as well, so you don't have people constantly changing the thermostat trying to cool the room off. And it mitigates the spread of airborne diseases because it's much more effectively able to push the contaminated air towards the returns and moving it away from the breathing zone. Side considerations, you can use displacement ventilation in both new construction and in renovations as well. The greatest consideration, regardless of the application, is you can only use it in where the room conditions allow. So though this could be the architectural features of the room or the loading of the room as well. But it does allow you to use previously unused spaces, such as underneath a TV set. You could place a supply diffuser right there. Best practices, displacement ventilation works best in high occupancy spaces with really high ceilings so that you can really get the stratification effect of the clean air at the bottom and for contaminated air higher up. Displacement ventilation decarbonizes by reducing energy at both the boiler and the chiller. And because there is lower airflow required, this opens up the possibility for using smaller ductwork as well, which leads to lower construction and materials costs. You want to start the coordination very early on so that all the trades and even more importantly, architectural, make sure everybody's on the same page so that everybody knows to look out for the different design. And so you can work with the architect to find more aesthetically pleasing diffusers since they're going to be in the breathing zone and most likely within eye level. So people are actually going to be seeing these. And you would want to begin the distribution design from the diffuser out so that you don't lead to, so you can make sure the diffuser setup works so that the room can be conditioned as you want. Also work with your friendly, experienced MEP consultant who has done this before. So, thank you.
All right, well, thank you to Jim and Taylor for those quick introductory presentations. We're now going to turn to round one of the debate. I have the privilege of serving as the moderator for this section. Audience, it is a good idea to pay attention to the arguments that Jim and Taylor are making so that you can help rebut them for round two of the debate. I am going to attempt to share my timer. So we have 10 minutes. Jim, I'm going to direct the first question to you. So Jim, we heard a lot just now from both you and from Taylor, a lot of information. The question is, at the end of the day, why is your technology, why is desiccant systems better for decarbonizing healthcare than displacement ventilation?
Well, Troy, I think, to be honest, what you have there is a false question, a false binary. Both are actually good. So that's the only bone I'm tossing your way, Taylor. But they're affecting different parts of the building, right? So where you have ORs and cold rooms that need to be cold, and where you have high outside air moisture loads, you need to be doing whatever you can to reduce the amount of cooling you're doing and reheating in order to control humidity in the space. And that's where desiccants can be very valuable. They might be applied, in fact, on the system that provides air for your displacement ventilation system. So in that sense, they're a precursor. But displacement does have its place as well.
Taylor, same question to you. We've heard a lot of details, but why is displacement better than desiccant system? What's your argument?
I would say it's better. I think you should pair both of them with the same system. But especially with displacement ventilation, there is double savings to be had from the lower airflow and higher supplier temperatures. Reducing the airflow leads to energy savings at the fans and the smaller ductwork and everything, so it's lower both operational and construction costs. And by having a higher supplier temperature, there's obviously less need for reheat and less need for cooling as well. So there's also savings at the chiller and the boiler.
If I may add on to that, that savings in cooling and delivering warmer air only applies when the outdoor air conditions are allow that. When you're in, say, Atlanta, Georgia, and it's August and it's extremely humid, the dew point temperature is very high, you can't deliver warmer air unless you have dehumidified it, and therefore you need to focus on a desiccant system to do that.
That'd be true with overhead mixing as well. So that's nothing specific for displacement ventilation. Granted.
Great. Well, these technologies sound great, but Taylor, to you, they sound great, but they're also fairly complicated. Part of being best is being put in use. How am I going to convince my finance team to pay for this, for my board to support it? How are we going to make displacement ventilation systems real?
By operational savings. There may be more costs up front with slightly more expensive diffusers and everything with that. But as long as you are spending a lot more coordination time up front, when it is much cheaper to make system design changes, things like that. Those are cheaper earlier on, and then any additional costs associated with buying different materials will be paid off in a short amount of time through lower energy costs.
Great. Jim, do you want to respond to that?
To respond to the same question, yes. The use of desiccants has been around for a long time, and so it's not that it's a new technology. It's just not commonly used because there's been an easier way to handle the moisture problem. But desiccants have been in use for some time. I used a desiccant wheel in a surgery air unit back in 2004, I think it was, maybe earlier than that. Desiccant wheels themselves have been around for decades. They were in place before I started doing this, and that was a few years ago. So they've been around. There is a little bit of a cost add for using a desiccant wheel versus the brute force method of cooling and reheat. But the reality is, to get something better, you sometimes have to pay a little bit for it. But if you do the math, and if you're able to save on the cost of the cooling system by putting it in a desiccant system, you can offset the difference. And then if you look at the operating cost, do an actual life cycle cost, the desiccant system will win, as long as you have a decent number of hours of high dew point.
Wow. Jim, let me make sure I heard you right. Are you saying that desiccant systems win on the life cycle cost?
Compared to a brute force system, yes.
Mm-hmm.
I'm not comparing that to displacement, because the two, you really have to do both in some cases.
Excellent. That's what I thought. You know, it's funny, both of these technologies seem amazing. They also seem like they're on the on the leading edge. And I've heard some folks in healthcare say, I like to be on the leading edge, but not on the bleeding edge. Jim, to you, what are the risks and pain points around desiccant systems? And given those risks and pain points, how can you argue that they are the best?
Well, there's no doubt that over the last couple of decades, hospital maintenance staffs have been stretched thin. They have literally been thinned out, and even as their buildings are growing, they have more to take care of. So anything that is more complicated to take care of should be looked at with a skeptical eye. However, we're talking about moving away from steam boilers, and everybody's comfortable with steam boilers, but they actually take an awful lot to take care of. There's a lot of work involved. One of the systems, what I was taught to do in the early days of my career to solve moisture issues was to use an air-cooled chiller, run it at a low temperature, and use that to dehumidify by subcooling, what I would call the brute force method. And what I've learned over the years is that people generally hate those chillers. They don't last very long, especially the modern versions with microchannel coils on them. A little bit of dirt and you start clogging that coil and it doesn't work anymore. And so there's maintenance on those to keep them clean if you can, and there's money spent to replace them when they fail much sooner than you expected. So there is an increased cost potentially in maintenance of a desiccant wheel, but that is offset by the things you're not having to do. And even if there's a small increase, if you take care of it, it'll function for decades and keep doing its job. So I don't think that's a major issue for these systems.
Right. Taylor, do you have a response to Jim, or would you like to make an argument for displacement ventilation and why it's the leading edge, not the bleeding edge?
So it is not even the leading edge. It's been around since the 1970s, so there's no reason to be afraid just because it could be perceived as a newer technology. It's just not as common. And because of that, because it's not a typical design for many spaces, there could be resistance from contractors or designers. But by beginning the coordination early on, starting those talks early on so everyone's on the same page, they become more comfortable and familiar with the design decision. And there's also plenty of resources out there from vendors and online sources for how to design around these systems.
Well, great. Thank you, Jim. Thank you, Taylor, for participating in this round of our debate. In a moment, we're going to go into breakout rooms in preparation for round two. Round two will involve a series of rapid fire sessions, 2 minutes each, where you'll have an opportunity to rebut arguments made by the other team and make your arguments even stronger. In a moment, participants, you will be assigned a team at random. A couple of notes that are meant to be encouragement. The first is that you'll have a better experience if you're able to turn on your cameras. So I suggest you turn on your cameras when you get into the breakout room, if able. Number two, this is an opportunity to dig into the guidebook. In a moment, either Jess or I will put the links to the guidebooks in the chat. You'll get them again in your breakout rooms, and you can literally dive in and create great arguments. Number three, while Jim and Taylor are champions, you will have the opportunity to champion your own arguments. So I encourage you to be vibrant, to speak up when we get back into round two, and to have a great time. Welcome back, everybody. It is time for round two of the debate. We are going to start off with our desiccant system team. Desiccant system, you'll have 2 minutes. I will get my timer up as soon as I possibly can, but you have 2 minutes starting when you say your first word.
All right, so we have no doubt that desiccant systems are the best way to go here. But we think there are a few flaws in the arguments that we heard previously from the displacement team. And so, Anna, would you lead us off there?
Sure, yeah. So there's some real challenges to displacement ventilation. The first one being that it's highly dependent on the vertical stratification of the air in the room, and that is totally dependent on the actual room loads, which can be modeled and attempted to be predicted up front, but are rarely necessarily what actually happens and are variable. So I would say its efficacy is in question. And also in terms of pandemic flexibility, we here at UCSF Health have been modifying room airflows and pressurizations in reaction to COVID, and displacement ventilation would make that much more challenging to be able to really be flexible with increasing airflows in the case of a pandemic. And just generally speaking, the document on displacement ventilation made some percent savings claims, but it wasn't clear whether that was just for the rooms that it's being applied to or whole hospitals. So I just want to make sure we've got an apples to apples comparison there.
The other thing noticed, I mean, it's right there in the chapter on displacement, is that sunlight striking the floor is a problem because that heats the floor and throws off the ventilation. So what we're proposing, what our colleagues on arguing for displacement are proposing, is that we limit the size of windows, which has an impact on patient care in a way that the displacement system can't compensate for. Did we have anything else we wanted to say? I guess there are some others that might be self-evident to those of you who are listening, but we'll stop there.
All right, displacement ventilation, you have 2 minutes to counter.
In the case of the solar heat load on the rooms, the beauty of displacement ventilation is that it's sort of heat seeking. The warmer air that's rising up as a result of the solar heat gain is going to need to be replaced by the cooler, denser air that's coming in from the diffusers, which would directly remove the warm air from the space, improving thermal comfort. And in pandemic ready, displacement ventilation is especially suited for that because it prevents the air from mixing in the room, protecting the occupants inside. The warm contaminated air, again, is displaced by the incoming air and pushed up directly to the ceiling instead of having an opportunity to mix with the rest. The debate here is about minimizing reheat. So by using lower airflow rates and higher supplier temperatures, there is plenty of savings to be had at the chiller and the boiler. Is there anything else we were wanting to add, team? Chris, you're on mute.
The other item with displacement is it doesn't traditionally have to go at the floor level or just above the floor. In the case of the hot window, you could also make that the location, because patients usually aren't by the window, to dump the cold air down by the window with something like an egg crate grill that'll slowly drop the air into that location and blanket the floor to be used at the heat loads at various locations with natural convection wicking up then.
Displacement ventilation, thank you for countering those arguments. You now have 2 minutes to make your own arguments and poke holes in the other side as you see fit.
So Chris, the floor is yours for 30 seconds.
Okay, so desiccant. One of the items that was brought up is the fact that maintenance staff has been cut bare thin. There's a lot of concepts and systems they don't fully understand. Desiccant is a hard one for them to comprehend. Most of the time it's being run by RH sensors, not dew point sensors. And a technician or maintenance person may not know if they have a problem or not until it's at the OR or wherever you're trying to dehumidify. And to actually track down what the problem is, it's not like a traditional unit where you can look at what your incoming water temp is, see the approach, see what your, see if you have an issue, check filters, the strainers and everything else. The desiccant system, you're pretty much reliant on the wheel, which means bringing in the manufacturer. And if the unit's been installed for a number of years, without warranty, what do you do? That wheel get basically contaminated and can no longer absorb the moisture. While it has benefits, there's a lot of drawbacks and complexities to it that may make it challenging for a hospital to operate.
Thanks, Chris. Josh? Or I can share your point if you like.
Oh yeah, about just about where the reheat energy comes from.
Yes.
Yeah.
That Jim just kind of skirted over, but it's actually an issue.
Yeah, I think if you can use site recovered heat to reheat to use on that regen stream, then it can make a lot of sense, but that adds complexity and cost to the project.
Great, thank you, displacement ventilation. We now have rebuttal from desiccant systems. You have 2 minutes.
Megan?
Yeah, so on the complexity of maintenance, we're looking at getting 5 to 15 years out of them, and the 15 would be with really, really regular maintenance. But even in the case that maintenance is not up to par because of the complexities of it, sorry, my dog's barking, 5 years is still what we would be getting with the displacement ventilation, and it's a lot cheaper maintenance-wise.
Who else wants to jump in there?
And yeah, Josh was saying about heat recovery, and it's he's saying, what if we don't have any heat recovery in the project? But pretty much now, the energy code pretty much requires you to have. It's very stringent, and it's very hard to have a big hospital or a project without having any heat recovery on it. So most probably there is going to be heat recovery on the project, either if it's an enthalpy unit or something of that sort. So yeah, that was response to Josh. Anything else, guys?
I would add to that we also can use exhaust air as part of our regen air, which is exhaust air is already at the dew point we want, so it can be very helpful. Anyone else want to jump in there? Well, go ahead, Anna.
Oh, I was just going to say that oftentimes institutions install extra chillers, low temperature chillers, just to accommodate ORs, and this would help prevent that, which would be a maintenance savings.
Also a first cost savings. And I would argue that, yes, there is some complexity in a desiccant system. Yes, it does require some additional education, but I, for one, choose to believe that our maintenance staffs are interested in learning and want to become better. And if we provide that education for them, then we can have them, they will take care of our systems.
Great. 30 seconds to close. Displacement ventilation. You have 30 seconds for your closing arguments.
Okay, thank you, Troy. Displacement ventilation is the ideal technology for minimizing reheat because you can use higher supplier temperatures and the possibility for lower airflow rates, and any pains that are associated with designing around a different system can be minimized by beginning that coordination early and get everybody on the same page. So thank you.
Great. DS, 30 seconds to close.
So as with displacement systems, it's a new way of doing things, and it's time to start thinking about new ways of doing things. Desiccant systems are a replacement for the system I was taught to do 30 years ago, literally. And it's time to move on and accept that things can be different and we can make improvements. And we are going to have to do that in order to decarbonize our systems.
Great. Give yourselves a round of applause, everyone. Thank you so much for participating in this debate. My hope is that you had fun, that you got to engage a different part of your brain, that you got a chance to look at the guidebook, and that as you look at the guidebook, you have an opportunity to make suggestions. And you're probably thinking now about the things that are missing or the things that could be expressed differently. We did this because we want to hear from you. And so you can reach out to anybody on the Decarb team, especially Austin, if you have suggestions. We'll be in touch in the near future. You guys know who won the debate. We don't have judges here, but I think ultimately we're all winners. So thank you so much. Have a great afternoon, and we'll be back at you soon. Take care. Bye, everyone.
Thank you.
Bye.
Sorry for being the timer guy.